Got it. You're done. Thank you.
So thanks for the organizers. They can speak. They can speak again. So the title of this talk is Angle Ranks of Abelian Varieties. It's the title of a paper that's joint with Taylor Dupuy and David Zurich-Brown. When I was originally planning to give this talk in 2020, this was going to be work in progress. But as of earlier this week, the paper is on archive, and as of this week, it's been accepted to Math and Nolan. So there will be one more post to archive once we submit the final version. Yes, this is. You can find the preprint on the archive. I guess I should say something about. I met Hendrik. So I was a visiting graduate student at visiting Berkeley in the fall of '97. So this was a period in my graduate school career where I was really unsure of what I was supposed to be doing with myself. And in particular, I was interested in these things you could call arithmetic, algebra, and algorithms. And I wasn't sure which of those three I should choose to focus on. And I think the most important lesson I learned from Hendrik was that all of the above was a viable choice. So this talk, I believe, will reflect all of the above. It will also, I mean, it'll be connected to Lenstra's work in a more direct way that we'll see in a moment. Actually, maybe I'll start by mentioning a few things that I'm going to talk about. Formulate 5 questions. These don't quite correspond to sections of the talk, but they will all be addressed. The first question that I'll have to answer is, what is angle rank? Start with the definition. Let's see what I'm done with this. 2 is, why do I care? Me personally. So we'll use the demo over here to answer that question. 3rd is, why does Hendrik care? And I'll show you that too. Hendrik has cared about this for a lot longer than I have. 4 is, how is it related to other data that can be associated to an abelian variety? And of course, since it's some sort of numerical invariant, there's a reasonable question about how to compute it. Say a little bit about that, particularly at the end. So let me start with the definition. So throughout this talk, I'm going to take A to be an abelian variety over a finite field. It was my favorite finite field. Although, as we'll see in a moment, this is property is going to be invariant under base change. And to simplify matters, I'm always going to assume it's absolutely simple. So it's simple over FQ bar. This question about angle ranks is, in fact, interesting when you don't assume that, but most of the theorems I want to state will assume this. So I'll limit myself in that way. So, so how do I make sense of the angle rank? Well, I'm going to make sense of it in terms of Frobenius eigenvalues. So the Frobenius eigenvalues of A, they're going to characterize it up to isogeny. So this definition is going to be isogeny invariant. So I'm going to label these. Well, so first let me give the dimension a name. The dimension is going to be G, because I habitually call that even when A is not a Jacobian. It will never be a Jacobian in this talk, but nonetheless, I'm going to call its dimension G, as if it stood for genus. So there are 2 G Frobenius eigenvalues, and I'm going to consistently label them in the following way. I'm going to have G of them be some choice, and then the other ones are going to be their conjugates. Listed in the same order. So alpha 1 through alpha G, and then alpha 1 bar through alpha G bar. Of course, the conjugates are well defined independent of a complex embedding because we're going to get a CM field in a moment. This one. So F is going to be the number field generated by all of these guys. Kind of split them separately because I don't really need to put the second half in, because alpha I times alpha I bar is always going to be equal to Q. So it's enough to put the first half in, and you already generate the others. Okay, so the angle rank is going to be some number that I define in terms of these eigenvalues. Put this up since I'm done writing on it. So I'm going to call this delta throughout the talk. So there's two different ways. Well, there are several different ways to characterize it. Let me first give you the definition that justifies the name. Namely, so I pick some embedding of f into the complex numbers, which won't matter. In order to not say wrong things, I have to pick one. So what I'm going to do is I'm going to take the arguments of these complex numbers, embedded alpha i's. I'm going to take the subgroup generated by those inside. Right, these are well-defined. Maybe I should write lowercase, so I don't mean principal branch. But, right, these are well-defined angles inside the group R modulo 2 pi z, sometimes called the angle group. And I want to take the rank of the group generated by these things. And I don't really need to go up to 2G. I could stop at G. So this is the rank of the group of angles of the Frobenius eigenvalues. That's called the angle rank. So that's one possible definition. But since I'm an algebraist, I would rather say this in a way that doesn't involve complex numbers in any essential way. So another way I can say this is I say, well, I just take the alphas and view them as elements of the multiplicative group of this field, and I just take the group that they generate after I divide out howards of Q. So that gives me the same thing. This, of course, you can see from the fact that I only need the first G generators, this is some number from 0 to G, and it's also independent of base change, or invariant under base change. If you do a base change, right, you raise all the Frobenius eigenvalues to some power, that is not going to change, right? You could think of these ranks as being dimensions if you tensor with Q. And so you're just sort of scaling all the generators by a constant factor. That's not going to change. Answer the first question. That's what angle rank is. Now, how did I get interested in this question of what angle rank is and what properties it satisfies? We are locked out here. The password is there. Okay, we're back. So this is the LMFDB, which we've heard about at least once already this week. So a few years ago, David Rowe, Taylor Dupuis, Christelle Vincent, and myself put together a database of isogeny classes of abelian varieties over finite fields for the LMFDB. What makes this feasible is, of course, the Honda-Tate theorem, which says that isogeny classes are basically indexed by Weil numbers. You have to be a little bit careful about the correspondence between dimension of the abelian variety and the degree of the irreducible polynomial. But basically, you can write down Weil polynomials, and that is tantamount to writing down isogeny classes. So, but then you can, once you have a table of isogeny classes, you can pick one and compute more information. So we built pages associated to isogeny classes of abelian varieties over finite fields that tell you interesting things. So, so I picked a random one. So I get, it's dimension 3 over some base field. This is the reverse characteristic polynomial of Frobenius called the L polynomial. So if this were coming from a number field, this would correspond to the Euler factor in the L function. And there's various things that we've computed, including the Galois group of the Frobenius eigenvalues. So we've computed the Galois group of this field F, and we've computed the angle rank, except we kind of cheated and we didn't really compute it, right? We computed what it looks like by taking this definition, computing all these things numerically, and then looking for relations using lattice spaces reduction. Not the reason why Hendrik is interested.
Yeah. Can I just ask a quick clarifying question? I'm having trouble parsing this first definition. What is the angle of J alpha I? It's just a
So this is a complex number, and I'm just taking its argument.
Oh, the argument. Oh.
Sorry, yeah, it's ARG for argument. I mean, I could have called it angle. When I wrote is ARG for
I
argument.
see. Okay, cool. Thank you.
Yeah. So in the picture, right? The 6 Frobenius eigenvalues are plotted. So you measure angles, counterclockwise from the right, and those numbers, of course, they come in pairs. And in this case, the 3 numbers that you get, I'm claiming, are linearly independent over Q. Of course, you can't prove that by this finite computation that I just did, because maybe there's some relation that's really huge and you don't see it. So we'll talk later about strategies that allow you to actually confirm the numerical prediction, which in some future version of the database, we will actually run over and confirm all these numerical predictions, but we haven't done it yet. And there's also things like the Newton polygon. And you can ask, well, how do the angle rank and the Newton polygon interact? So we did a calculation over all the data we had to look for example, that we considered the P rank, which is the 0 part of the Newton polygon, and the angle rank, and we asked, well, which values of these 2 numbers do we see in the table? And we saw there were some missing values. And we said, that's interesting. I wonder if anybody knows about this. And of course, one person who knows about this is Hendrik. Look at that shortly. So the reason I got interested in this question about angle ranks is that we were tabulating this data. I think Taylor was interested in angle ranks for a different reason, which I won't go into. But he got me, so he wanted to compute this. So we computed it, and then we saw there was some non-trivial interaction with other data we had, and we wanted to understand what was going on. So we started ransacking the literature, and then we got some explanations for things we were seeing, but not everything. So we decided we needed to sort of write things down systematically. That's the source of this project. So that's how I got interested in this. All right, so maybe, unless anybody wants to ask questions about the demo, I'm going to shut this down so that I have the other half before. But this is a good time to pause to, if you want me to demonstrate anything more. Twice. All right, I'm going to go full board. Talk. Of course, you're always welcome to ask me afterwards if you want to find out more about it. Okay, so let's go back to doing some theory and look a little bit more at possibilities. Well, first of all, let's look at the extreme case. So let's look at the case delta equals 0 for a moment. So this is a fun exercise in algebraic number theory. Delta equals 0, I claim, if and only if A is supersingular. So that's true without the absolutely simple hypothesis, but because I'm assuming absolutely simple, this actually has to be right. If you're supersingular and you're absolutely simple, you actually have to be an elliptic curve. So G equals 1. In this case. So a lot of theorems are going to be stated excluding G equals 1, and so this case will just not occur. Right? Maybe I can tell you a little bit later if you haven't figured out the exercise button on how to do it. I encourage you to think about this if you've never thought about this stuff before. It's quite an elementary thing. Okay, delta equals 1 I won't say this out, but there's a simple classification. At least in terms of the, I mean, you can say quite explicitly what the Weil polynomials are in this case, because this is saying that the ratio of any two Frobenius eigenvalues is a root of unity. So that leaves very little wiggle room. There'll be some cases where you can, if delta equals 1 shows up as a possibility, you kind of manually rule it out. So the other extreme is, of course, delta equals G. This is the generic case in some sense, meaning if I actually checked LMFTB, I'm pretty sure something close to 100% cases would have delta equals G. So this is the thing that happens the most often. And and why is it important whether or not delta equals G? Is because this has something to do with the Tate conjecture. So delta equals G is equivalent to saying that the Tate conjecture holds, well, it's not just saying that the Tate conjecture holds for A, or better way to say it is I consider all powers of A, and I say the Tate conjecture holds for all powers for A for codimension 1 reasons. So reminder, the Tate conjecture says, well, for A, let's say, for A, I mean, the Tate conjecture is a statement about arbitrary, say, smooth projective varieties over finite fields, but let's just formulate it for A, and then the similar statement for powers of A, is that if you take some even degree cohomology group, say X base change FQ bar with QL coefficients for some prime L not equal to P, no matter which one, well, the conjecture is not formally equivalent, but for the sake of formulating it doesn't matter. Okay, so this, of course, has, since I base changed to FQ bar, I have the Q power geometric Frobenius on it. And the claim is that the generalized Q to the I eigenspace, so is spanned by cycle classes. So the presence of the eigenvalue Q to the I and H to the 2I is completely explained by geometric objects, maybe codimension I cycle classes. Yes.
Conjecturally, you don't have to write generalized as well.
Correct. If you actually could prove the Tate conjecture, you can then this right. If this were true, then these would all be true eigenvalues. So you would remove generalized. But
What is the exponent at Q?
Q to the I.
What is I?
I is the same. This I, H to the 2I. So so these are codimension I cycles. So this I, and this I are all the same. Right? Okay, and this is, of course, true for I equals 1 by Tate. Right? This is the Tate part of the Honda-Tate theorem. It's a harder problem for I greater than 1, but if all of the generalized QI eigenspaces are explained by, powers of things in codimension 1, then that certainly implies the Tate conjecture, and that turns out to be what this condition is saying. In the literature, I think this is Zarhin's term, but maybe Hendrik can correct me. These conditions are sometimes called saying that A is a neat abelian variety. So if you find cases where you can guarantee that delta equals G, you've found cases where the Tate conjecture is known to be true for kind of an easy reason. Of course, the Tate conjecture is sometimes true for a harder reason. But I just want to focus on the cases where it's true for an easy reason. So now this brings us to sort of two classic results. I'm going to say classical because that implies they're old. I'm going to say classic in the sense that they're good. So the first one is a result of Tonkaev. This is from 84. So I'm assuming A is absolutely simple, remember. If G is prime, then delta is limited to very few possibilities. Namely, it could be 1, G minus 1, or G. Remember, 1 is quite a restrictive case. For instance, if you know that the endomorphism algebra of A is a field, then this case drops out as soon as this case drops out. So most of the time you're saying that delta is G minus 1 or G. And then the other result, so very beautiful paper of Leinster and Zargan, I think is 93, which is that if A is almost ordinary, which, i.e., the Newton polygon consists of the slopes, bunch of zeros, a single pair, a half, and a bunch of ones. Well, this case will break up into two possibilities. If G is odd, then delta can again be either G minus 1 or G. And if G is even, then first possibility is excluded. So this almost ordinary condition, I guess this terminology is due to Oort. It's codimension 1 in moduli, because this is what I've done is I've taken the standard Newton polygon and I've chopped off a single vertex. So it's the codimension is sort of the number of lattice points you kind of raise this thing relative to the generic one. Symmetry. So this is codimension 1. So this codimension 1 condition plus absolutely simple has a strong consequence for this angle. So these two things together explain a lot of things we saw. So for instance, we have examples in LMFDB of we have all the dimension 5 varieties over F2, and we could certainly see this happening numerically, clearly. And we could also kind of detect this. This was definitely reflected in the data. So, of course, they were theorems long before they were numerical observations, but they are consistent. I'll just mention that these not equal to G possibilities do occur. So, for example, when G equals 3, you can look in the LMFDB and find cases where you hit 1 or 2, and you can find almost ordinary cases where you hit angle rank 2. So in that sense, these statements are best possible. It's not that I've just missed a trick. And I should somehow be able to prove that I get angle rank G. There really are, under these hypotheses, this is really the most you can say. But of course, in individual cases, I claim you can often say much more. So again, most of the time, angle rank is G. So from a point of view of, so coming back to this computational question, right? I have a lot of abelian varieties in the LMFDB. I would like to turn those numerical angle ranks into rigorously computed angle ranks. Well, most of the time, the answer is going to be G. So it would be really nice if I had a very, very cheap test that can, when it works, hopefully it works most of the time, and when it works, it certifies that the angle rank is equal to G. Because then I'll just run that test on everything and then just deal with what's left over. So, in fact, there are several criteria that are satisfied most of the time that will certify this. And they are most easily stated in terms of the Galois theory, this field F. So let me proceed to that. So we've answered the first three questions. I guess we've also said something about the fourth question. Now I want to gain more information about how to do the fifth question. Forget how to balance these. So before I say anything more about computations, let me tell you about a key ingredient in these arguments, or at least in the arguments. I guess this is, so Tonkayev's proof is really secretly well, not so secretly. It's a paper about Hodge theory. So there's some relationship between abelian varieties over finite fields and CM lifts, which I won't say too much about. But if you read Tonkayev, you have to kind of translate if you want to directly state arguments in terms of finite fields. But this is sort of what you get when you do that. So I still have the Frobenius eigenvalues on the board. I'm just going to reduce the data a little bit. I'm going to write beta I to mean alpha I divided by its conjugate. So this is a totally real algebraic integer. And I still have G. So G is going to be the Galois group F over Q. And
What did you say about totally real?
alpha I divided by its no, this is totally, what is it? Sorry, it's norm one. Yeah, it's the other way. It's norm one, so it's not totally. I'm just going to use this as an algebraic quantity. I'm never going to think about it inside C's.
But it won't be an algebraic integer usually.
No, it's just an algebraic. Sorry. Yeah, so it's neither totally real nor an algebraic. Right. But it is in the multiplicative group of F, and that's what I care about. Really, it's in the totally real subfield of F. So I'm going to define the following thing. So now I'm going to use valuations on F in the following way. So I'm going to define V to be a subspace of Q to the G, which is the span of the following vectors. So I take the valuations of beta 1 through, I should have said somewhere, the angle rank, so exercise, it's not very difficult. The angle rank is equal to the rank of the group generated by betas inside F star. So this is sort of, I don't have to divide out by Q anymore.
So is that also true if I just look at the ideals generated by the beta I?
Yes.
Okay.
Yeah, I mean, that'll be implicit in the thing I'm about to say here.
Oh, okay.
Right. So you take, so I can also characterize the angle rank in the following way. I take these vectors for all places B of F above P. There's a whole bunch of places of F above P. I take the kind of valuations of these guys, and then I claim, and again, you have to check this, but Hendrik has sort of anticipated this already, is that this delta is equal to the dimension of this Q vector space. That's more or less equivalent to the affirmative answer to Hendrik's question. So for example, if angle rank is 0 is the same thing as saying that this space is the 0 space. And so this ultimately comes down to the fact that if you have
Supposed to last for about 20 seconds.
concludes our halftime presentation on the proof of the Riemann hypothesis. Tune in next time for a different halftime quiz. So this, yeah. So if your dimension 0, that's saying that these algebraic numbers have all p-adic valuation 0, and of course they all have real absolute value 1, and their prime to p valuations are all 0, so they're forced to be roots of unity. So that's the proof of that's the solution to the exercise. Great. right, so let's actually talk through now I can sort of tell you how to prove these two theorems. So first of all, let me point out that G, the Galois group of F over Q, acts on this set of vectors because it acts on the valuations. So this forms a a rational representation of G of rank small g, dimension small g. And well, so the proof of Tonkiev follows by observing that, well, if G is prime, then G has to divide the order of this Galois group because it has a transitive action on this prime number of things. And so you have a cyclic group of order G acting on Q to the G, and the only sub-representations are the fixed subspace and its complement. So that gives you Tonkiev. Now, for Zarhin, what you do is you say, well, these vectors mod 2, let's say M is let me let M be the matrix formed by these vectors. So up to kind of reordering and shuffling things around, right? When you're almost ordinary, these vectors will all be integer vectors consisting of a 0 in one place and plus or minus 1 elsewhere. So when you reduce mod 2, you get and you kind of remove redundancy and sort things out to be nice, you get a matrix with zeros on the diagonal and ones everywhere else. And delta is bounded from below by the rank of this mod 2 reduction. There you are. And so, of course, you also observe, as Zarhin did, that if the slopes have the same two-adic structure as this example, namely you have 2 1/2 and everything else is a 2-adic unit, then the same argument works.
The order of the group G.
I haven't, well, I'll tell you in a moment about the group G, but for the moment, right, all I've used so far is the fact that it acts transitively on these G numbers. So that puts a factor, if G is prime, that puts a factor of little g into that order. Let's talk more about this group G because we can say a lot more if we actually pick apart what this G is. Right, because it doesn't just act on the betas, it also acts on the alphas. And all right, so the way to think of this group is so G bar is going to be the permutation group acting on the betas. So that's a subgroup of SG. So G bar is gal F, real subfield F plus. You?
But the betas are not lying in F plus.
Yeah, it should. That's true. It's still the group that acts, right? Because it's the yeah, right. It's better to say that this is the action on the pairs rather than, but that is the same as the action on, alpha I plus alpha I bar. So
Yeah.
so it is canonically isomorphic, but maybe does it make you happier that it's not equal, but it's canonically isomorphic?
So G bar is by definition what?
It's going to be the yeah, it's going to be, so it's the image and G in the permutation group on pairs.
Okay.
That's how I want to think of it.
So that is beta I plus beta I bar or something.
Well, I'm thinking of it alpha I plus alpha.
Yeah, should really be the same, right? Anyway. No, maybe not.
Yeah, maybe up to. Okay, so there's so this thing is by definition going to be a subgroup of SG.
But beta I times beta I bar is 1, so it
Yeah.
should really be the sum. That's the only coefficient that is left.
So right, G is by definition is a group of permutations of the alphas. So, right, as we've kind of already alluded to, that action is imprimitive because alpha I and alpha I bar pair to a block. So I have some grouping here, which this is going to be I'm going to think of this as signed permutation matrices. Implicitly going this I was implicitly splitting this exact sequence. You don't want to do that, but if you want to see what this is, this thing in the middle is going to be the group of signed permutation matrices. And so inside it, it has the group of signs, which is an F2 vector space dimension G with a distinguished basis, right? Because what I'm doing here is I'm looking at each pair alpha I bar individually and asking whether I flip the sign, or I conjugate that pair, or I don't conjugate that pair. So this is really canonically F2 to the G, not just an F2 vector space. G. And so this thing is going to embed into here, and there's going to be some kernel, which I'm going to call C. And I'm calling it C because I'm also going to call this thing the code of A. And I'm calling it the code because it sits inside F2 to the G. So I'm thinking of it as a binary linear code. Not that I'm going to use any serious coding theory in this talk. It's just a useful metaphor that I have this F2 vector space with a fixed basis. And I'm going to care about things like, weights of code words and so on. But yeah, so this is calling it the code is sort of shorthand for remembering that it comes inside an F2 vector space with a fixed basis. Okay, so yeah, and so generically, this middle map is an isomorphism. So G is equal to this semi-direct product, and that will force angle rank G for the following reason. So maybe before I say what the reason is, let me point out that there are sort of two different actions I have in the picture. G acts on V, this Q vector space, dimension V, little g, and G bar acts on this F2 vector space of dimension G. Now, of course, I can't explicitly say that if I take I'd like to say something like, well, I take this representation and I reduce it mod 2 and it factors to G bar and I'm getting this representation. Well, that's not a totally well-defined thing because, these vectors are not two-adic units in general, so I can't just reduce them. But in some less concrete sense, it is going to be the case that if you take the representation V and somehow reduce mod 2, you're getting this representation of G bar. So these two representations are going to be very closely linked. And maybe I should also mention this C is not 0.
Yes. If you had defined V to be the subgroup generated by those vectors, would you get closer? Then you can at least reduce modulo to V, right?
Yes. I didn't think about what happens when you do that. But yeah, you could sort of, take the Z subgroup, just subgroup generated by these vectors. I didn't think carefully about what happens, but it might end up. I think it actually is the case if you do that and you reduce mod 2, you're getting, that you have to, that's too big, right? That's going to be bigger than dimension G in general.
Up to semi-simplification, maybe.
Yeah, probably up to, I didn't work that out. But you can probably make that precise. The comment I did want to make is that C is of course non-zero because, the Frobenius eigenvalues maybe I should be assuming that. Unless I'm probably going to forget to say this from now on, I should assume that G is greater than 1. To rule out this silly case about supersingular curves. So as long as I do that, then C is non-zero because the alphas are not real. So there is there is little c in here, complex conjugation. I alluded to that earlier. So C is non-zero because it contains complex conjugation, but it could happen that that's the only thing it contains. And so when that happens, I'll say C is trivial, and otherwise I'll say it's non-trivial. So the subtrivial means that it has the thing that it's forced to be in there. Let me write. C trivial means it's just the span of complex conjugation. Capital C is trivial if it's spanned by complex conjugation, and non-trivial. Okay, so let me say something that implies this claim that when G is big enough, I have to have maximal angle rank. And so this already will give me coverage of close to 100% of the cases in the LMFTB. Right. This will, the way I'm going to say it will also cover a lot of the more degenerate cases. Lemma. So I partition, right? The indices of the code are and I've kind of labeled them 1 through G. So I'm going to partition this into TIs according to the evaluation functional. Meaning, right, two indices are the same if they define the same evaluation functional on C. So if C is full F2 to the G, then you know, any two indices define distinct functionals. And so then I just get the trivial partition where everybody is isolated. And notice that G bar, this is a block decomposition of G bar. So then I claim that that same partition defines a partition of V. I guess it defines a direct sum decomposition. VI. VI is the intersection of V with the subspace of Q supported in the coordinates of TI. Right. So just to say this in a less highbrow way, right? I have a canonical basis of V and I have a partition of that basis. I use that partition to define a subspace decomposition of Q to the G, and that induces, you know, well, it doesn't a priori induce a decomposition of V, but the claim is that it does.
What do you mean by the direct sum sign?
This is the sum over, right? Q to the sum TI means you take the copies of Q indexed by the elements of TI.
So there is no sum over I. Okay, good.
Yeah, it's the sum over, well,
Elements of TI.
yeah, so there are M of these summands, one for each partition. And now the point is that this G acts on the, so I have this sort of Q blocks and G acts on these. So for example, if M equals G, right? That's when the code is maximal, then everybody is in its own part. when m equals g, then I have this representation. When these spaces are all isomorphic to each other because they're transitively permuted by g. So either they're all 0, which is the supersingular case, or they're all one-dimensional, in which case I get. So either I'm in the g equals 1 case, delta equals 0. Or I have maximal angle rank. So this covers even more cases than just asking for the Galois group to be maximal, or even just asking for the code to be maximal. And you can also, I'll also point out, because right, this is a block decomposition, the number of, right, the size of each block times the number of blocks is g, so m divides g. So and it also, of course, it also divides the angle rank, because V is a direct sum of m subspaces all of the same dimension. The angle rank. So for example, if I am in one of these situations, if I have one of these theorems from earlier, and I have this lingering possibility that delta is g minus 1, then I must have m equals 1. But what does m equals 1 mean? M equals 1 means that any two indices define the same evaluation functional. Well, there's only one way that can happen. That can only happen if this code is trivial. So the only element of the code is complex conjugation. And yeah, that's quite rare. It's actually quite difficult to produce Weil polynomials with this property. I tried. Great. So I'm going to state two more things I want to get to in the last 10 minutes or so. I will say while I'm erasing that the story of this topic is certainly not complete in our paper. I think there's still quite a lot more one can say, but I will limit myself to two more things. One. So this is kind of a sample of what you can do even in the situation where the code is trivial. Yeah, let's say I'm in the situation where m is 1. The typical, because let's say I'm in a situation where I couldn't distinguish between rank m and m minus 1, including g minus 1. So say g is greater than 3 and e bar acting on, right, it acts on a set of indices. Say it's 2 transitive. So, I mean, it has to be transitive. But let's say it's a little more than that. Let's say it's 2 transitive, then delta can only be, well, okay, this theorem is not going to take apart g minus 1 and g, but at least it's going to exclude any other possibilities. Right? M equals 1 doesn't automatically exclude any other possibilities, but even when so you could sometimes exclude possibilities based on m, but even when you can't, you can sometimes exclude possibilities based on g bar. So kind of both sides of g, the sub and the quotient, are trying to push the angle rank up. The bigger they get, the bigger the angle rank gets. So again, this knocks out in more cases that you might find. Maybe. And the last thing I want to do is talk about strategies for rigorously computing this angle length. So I mentioned this problem earlier. So it's easy to guess delta numerically, because if you compute the angles to enough precision, you'll see some relations quite quickly. Of course, if you see a relation and you've computed it numerically, you haven't proved that that relation exists, but you can go back and find the eigenvalues and actually prove that equality without so much trouble. The only trouble is that F is potentially a kind of large degree number field because it's the Galois closure. So there's a bit of an issue there. So we're thinking some about strategies where you don't have to actually go into the Galois closure, but let me not dwell on that. The question I want to focus on is sort of the opposite question, not of proving that relations exist, because I have at least an algorithm for that, even if I have to do work to make it efficient. But I need to think about, how do I prove that relations don't exist? Well, sometimes I manage to prove that delta equals G, but sort of in parallel, let's say I don't I get a sort of mired in group theory, and I'm not able to prove that way that delta equals G, or I just want to state a condition that and a theorem that doesn't involve kind of hardcore group theory. Is there some way I can certify in some more direct way that I found all relations? And in particular, I'm going to ask the question, can I bound the, say, L1 norm of a vector, of generating vectors E1 through EG in the group? Well, so I take all of the vectors, so I take the group of relations among the first G Frobenius eigenvalues. So I'm going to take all the integer vectors in Z to the G such that alpha 1 to the E1 times alpha G to the E G is a power of Q. It's slightly convenient to allow minus sign as well, so purposes of stating the actual numerical answer. So I want to show that this group is generated by its vectors of bounded L1 norm. And so that in principle would give me an algorithm, because then I just sort of do what I check for some finite set of vectors, which ones are relations, and then I take the span. And so when we were starting to think about this project, I asked Yuri this question at the Simons collaboration meeting in January 2020, and maybe within a month he had the answer. I guess I should put 22 because the publication date is 22. Yes. So Yuri's theorem is, yes, there is a bound. Maybe I should say in terms of P, I don't want this to depend on Q. I mean, it's easy to bound it in terms of Q. That's kind of silly. So I want this bound just to depend on G. And so Zarhid's theorem is that, yes, there is a bound, depends on G. Of course, there's a natural question you would want to ask, which is, what is it? Or can you give me a bound? And so here is an explicit bound. So I'm going to write it not as a function of G just to make it sharper, but everything in it can be bounded in terms of G. So I'm going to leave the angle rank in the bound. The angle rank is of course bounded by G, and M is going to be the common denominator of the Newton slopes. Which in principle I can bound by something like G factorial. But in most cases of interest is much closer to 1. Since in the ordinary case, M is 1. So if M is if A is ordinary, then this bound, you replace delta by G, you get G to the G plus 2.
So what is the name in front of the gear number?
Us. So maybe I should write the more conventional thing would be to put initials here.
Okay, just fine.
Us was shorter than writing 4 initials. So this is a theorem from our paper that you can take this to be the bound. Now, this bound is probably not anywhere near sharp. If you actually do examples, you find, okay, right, the minimal weight of an interesting relation is going to be probably, in this notation, it might be 2. You could have the minus sign, and you could get 2 with the minus sign. In practice, when you look in the LMFDB, the relations tend to be very, very low weight. So once you go up to weight, 5 or 6, you found all of them. So there is some interest in figuring out how to improve on this. Now, of course, you could also try doing this with Baker's method. I think what we're doing to prove this is somehow some kind of shortcutted version of p-adic Baker's method. So I don't think Baker's method directly is going to do better than this. I think it'll actually do worse. But there's clearly some room to improve here, and it would be interesting to think about what's a much better algorithm that can actually certify what the angle rank is once I've numerically guessed. So I'll leave that as a problem for future consideration. Let's stop there.